Okay, in this one I wanted to show you a way to optimize memory access on Linux with huge pages. So if you know, Linux has memory pages that are mapped into your process whenever you, for example, malloc, or if you open a file. Well, if you open a file in a particular way. And so, yeah, those memory pages are 4K long, and since your process has virtual memory, so it's virtual memory is the OS makes it look to your process like it has all the memory, but in real life, the addresses of your process get translated to real addresses, and this translation can take a while if you're using a lot of memory, especially if you have a big pool of memory and you're accessing and writing in this memory at random places. What happens is that every time the OS has to do the translation, because there is something in the hardware to do this translation, a cache, if you will, and this cache has limited space, and so if you have too much memory, too much of these pages mapped into your process, well, some of those pages addresses are going to be evicted from the cache. And so if you try to write to something that isn't in this address translation cache, it will need to pull that back from memory and put it back in the cache and then also translate your thing. And that takes a while. So anyway, I have a little example to showcase this. Here I malloc a lot of memory. I think this is 4 gigabytes with mmap. If you don't know what mmap is, I'll cover it in another video if you want to. But basically, in this case, let's just consider that mmap is basically malloc. This is what malloc calls under the hood, by the way. And so I just mmap, I just allocate these 4 gigabytes. And then what I do is that I just have a little timer to know how much time it took. And I write to random places in this memory. So this weird code is just a fast random number generator. And so I write at a random offset, I think it's, I don't know, millions of times. And so now we can showcase the naive approach, like so, and then let's run it. On this computer, I think it takes about 9 seconds, like so, or more. Or more, apparently. And so, yeah, we can see that it took 11 seconds. And so now I will use huge pages. So what mmap did in this case is that it allocates 8 gigabytes, but in pages of 4K. And so there is this huge amount of pages that have to be cached and so on in this special TLB. And so, of course, they get evicted because I do random writes to them. But you can have huge pages, and what huge pages are, well, it's kind of in the name, it's just pages that are larger. So instead of being 4K in size, they are 2 megabytes in size. And there is also another category of huge pages, which is 1 gigabyte in size. And so to use this, we have to provide a flag to mmap, which is called huge TLB, and another flag which is called map huge oh, actually that's it. That's huge TLB, and we have to OR it with the other flags. And yeah, and so your system has by default it doesn't have any huge pages. This is how you can know if it has any. You just get meminfo and then you search for huge, and then it will say the number of huge pages that is available on the OS, and in my case it's 0. And you can allocate some like this. So this, oh, I will, okay, just type my password. This is how now I allocated 600 huge pages that are 2 megabytes in size. And so now this should work. And so now if I recompile my thing and rerun it, Okay, I just made a small mistake because in one of my earlier examples I used 1 gig instead of 4 gigs, but so I need to allocate more huge pages that are 2 megabytes in size. So this is how you do it. You will notice that if I go in htop, like my memory is already occupied, because when you allocate a huge page, it actually reserves that amount of memory. So like other processes cannot use this huge page, or like if the huge page is not mapped to anything, well, it's useless. Nobody can use that space. It's reserved. So anyway, now that I allocated enough huge pages, I can rerun my example. And this time, last time it took 11 seconds. Now we should see that it takes, well, 7 seconds. So you can see that this is a very significant boost just by having this huge TLB flag and having a bunch of huge pages. So if your application has a very large pool of memory and you're using that memory in not an obvious pattern, so not sequentially, or I don't know, you don't use like specific 4K blocks at a time, then this is very useful because you will just gain speed for free. There is also the 1 gigabyte version of this, and to use it, you just have to add one more flag. So right now, we just used the 2 megabyte version, but you can add this huge 1 gigabyte flag, and it will use the 1 gigabyte version. And I think I need, actually that might be okay. Let's see. But in my case, since I only use 4 gigs, like there is diminishing returns, obviously. Like going from 2 megs to 1 gig page size is not that significant. As you can see, it even took a tiny bit longer in this case. So in this application in particular, it made absolutely no difference. I assume if you're the NASA and you're having like, I don't know, crazy universe simulation that take, I don't know, 2 terabytes of RAM, then these kinds of things might be useful to you. So anyway, I hope you appreciated this little showcase of huge pages and why they are useful. I think I will do one last thing before we leave, is just showcasing maybe to prove that this is why it went faster. I can do maybe something like, so this is the, oops, this will now be the 2 megabyte version, and we can see with this command, okay, the command was much more complicated than what I remembered. So perf, if you don't know, is a little tool on Linux so that you can observe your process, and so you could see like the number of CPU cycle or the memory used, or in this case, the TLB stuff. So TLB is the cache I was talking about, so it's the very fast hardware cache to do address translation. And so we can see that in this case, the TLB misses is this number, and TLB store misses is this number. And I will remove the huge pages. So, and we will recompile this, and we will rerun this, and we should see much higher numbers in a couple of seconds. So yeah, as we can see, the store misses are higher, the load misses are much higher, and well, basically every number here is higher, meaning that there was a lot more eviction on this cache, and that's why it was faster with the huge pages. Anyway, that's all I've got, and let me know if you want more videos like this about performance and using your OS in the best way possible. And I'll see you in the next one.